In this video we're going to look at similarity and frustums. Now frustum, first of all, is this shape over here where you have got a cone and then the top of it has been cut off. So the pointy end of the cone has been cut off and it is left with this sort of lampshade type shape, or if you turn it upside down you would imagine it could be a bucket or all sorts of different things. So it's a very useful shape and we're going to look at how we get at frustums and how they relate to similar triangles. Okay, so first of all, if I just redraw this shape up here, but I'm drawing it as if I'm looking at it from a side view. So, and I just cut it off like this. So there's the top triangle and the bottom triangle, not very well drawn, doesn't matter. The big triangle and the small triangle both share this angle. And then if you imagine this line here is parallel to this line. So that means that this angle and this angle are corresponding angles, and also this angle, give it 3 lines here, and this angle are also corresponding angles. So this small triangle, if we just highlight the small triangle, this small triangle here is a similar triangle to this bigger triangle here. So the small triangle and the big triangle are both similar triangles. That means if you know any of the dimensions on the small triangle and the corresponding dimension on the big triangle, you can hopefully work out a relationship between to go from small triangle to the big triangle, or in this case, the small cone to the big cone. Now here it just says if one of R, L, or H is known, we can use a right angle triangle to find the unknown using Pythagoras' theorem. So here, the perpendicular height is quite often useful, the radius, and then you've got the slant height L of your cone. So L is your hypotenuse, so L squared equals H squared plus R squared. And then you imagine if you had your cone, if I just drew in the other side of it, you can imagine if you have just this half of it, you can see that's a shared angle which we talked about here. That's 90 degrees as well, that's 90 degrees. And then that was another one of our corresponding angles. So you can see, but it's the same thing as the way I had shown it earlier on. Okay, let's look at a couple of examples here. Now that we know that the smaller cone is a similar triangle with the bigger cone. So the first example says, calculate the volume of the frustum to 3 significant figures. So basically what we want to do, the volume of the frustum is this bit that I'm about to shade in. So that's the frustum. So if you imagine what the frustum is, it is just your volume of the big cone minus the volume of the small cone. So that's really what we're going to do. So we'll just write that in. Volume is equal to the volume of the big minus the volume of the small. So we need to work out those two things. So have we got enough information to find the volume of the big cone? We actually do. We could work out the volume of the big cone because we've already got the diameter, so then we could half this to get the radius of the big cone, and we've got the height, so we could actually work out the volume of the big cone straight away. What we don't have, unfortunately, is a radius of the small cone. So the radius of the small cone is what we're missing, so we need to calculate it. Okay, my height of the big is 40, and it goes to the small one, which is 20, and it goes there by dividing by 2. So that means if I label this R in here, my radius of my small cone, it is just going to be the radius of the big, and I've almost made a very silly mistake there. The radius of the big, and the big one has a radius of 15. So if you divide it by 2, you're going to get the radius of the small, and 15 divided by 2 is 7.5. So we now know the radius of the big is going to be half of 30, so it's 15. The radius of the small is 7.5. The height of the big is 40. The height of the small is 20. So we're going to say we'll do all our working out here. Volume of the big is equal to 1/3. Sorry, I'll just write that down. Remember, the formula for the volume of a cone is 1/3 pi r squared h. So the volume of the big is 1/3 times pi times my r, which was, what did we say it was, 15? 15 squared times my height, which is 40. And I'm going to do this on my calculator, and if the calculator lets me, I'm going to leave it in terms of pi, because that's a perfect answer. And the calculator has given that as 3000 pi. And as I said there, that is a perfect answer, so leave it as that. My volume of my small cone was again a third times pi times my radius, which is 7.5 squared, times my height, which was 20. And again, I'll pause the video, do that with my calculator, give my answer in terms of pi. And that works out to be only 375 pi. So my volume overall is 3000 pi minus 375 pi, which is 2625 pi, which is equal to, I'm going to give my answer to 2 decimal places, 8,246.68, and the units, what are we in, centimetres, so it's going to be centimetres cubed, and that was the 2 decimal places. Okay, next example is quite a bit of work needed. In this one, you have to find the volume and the total surface area of the frustum to the nearest whole number. So, they've given a wee formula up here, it's been very nice, and giving you the formula for the curved surface area of the cone is pi RL. So that's pi times the radius times the slant height is what the L stands for. I think I mentioned that earlier on. So we will have a few dimensions to work out. Also for the volume, you need the perpendicular height. So we've got only partial height here. I'm going to call this height, this wee height, H as well. And then we're going to do a wee bit of working out. So to get from, I'm going to go from small to big. So 4 goes to 6 by multiplying by 1.5. So that means my height of H goes to my total height, which is all of this, so H plus 5, again by multiplying by 1.5. So let's just work that out. It's going to be 1.5 times H is equal to H plus 5. Bring a little bit H across to the other side, of 1.5H minus H is equal to 5, or 0.5H is equal to 5. So our missing dimension is 5 divided by 0.5, which is 10 centimetres. So we've now got the height of the smaller cone, if you can imagine. What we also need to find for our curved surface area is L. So we need to work out our slant height L. So I think I would just do these both using Pythagoras. So I'm going to look at this small triangle here. You can imagine I'm looking at this small triangle. So if I look at that small triangle, and I call that L1, and I'll call the bigger one, I'll just draw it on the other side just to avoid any confusion. That's L2. So if we look at L1, to find L1, I'll just draw that wee right angle triangle again. It was, the height H was equal to 10. So my height is 10. I've got my L1, and that is 4. So L1 is going to be equal to the square root by Pythagoras, skipped a wee step here, but square root by Pythagoras of 10 squared plus 4 squared, which is going to be the square root of 116. If I just put that into my calculator, it might cancel down a wee bit. It cancels down to 2 root 29. I don't think that's any use to me doing that. I'm just going to leave it as it is. So it's square root of 116. And my bigger triangle, so this is, if you imagine I do it, big triangle all the way down to here. So this big triangle, my radius is 6. I have my total height, my total slant height here is L2, we've called it. And my total height is 10H, which was 10 plus 5, so it's going to be 15. And it is going to be equal to my L2, and I'll show you there's another way I can do this, a smarter way I can do this to be quite honest. 15 squared plus 6 squared, and then my L2 is equal to the square root of 15 squared plus 6 squared, and that gives me 3 root 29. Okay, now if we have a wee look and see, remember when I did this earlier on, square root of 116, which I said wasn't going to be much use to me. It would have been if I'd been a wee bit smarter. That was my slant height of my first one. remember what we're talking about. We're talking about similar shapes here, similar triangles. So, and remember we said to get from the small to the big, we multiply by 1.5, and L1 is on the small triangle, and 2 root 29 times 1.5, of course, would give you 3 root 29. So I could have used similar triangles to that, but I just decided to do it using my Pythagoras in both cases. Wouldn't have lost any marks, but definitely would have been quicker to do the other way. Okay, we need to find our volume of the big and the volume of the small, and then we need to take them away to get the overall volume, and then we also need to find the total surface area, so a wee bit more work to it. Okay, so our volume overall is going to be equal to the volume of the big minus the volume of the small. I showed the working out for this in the previous one, so I'll skip this a wee bit. So the volume of the big is 1/3 times pi times r squared, and my radius of the big was 6 squared, and my height of the big thing overall was h plus 5, so it's going to be 15, minus 1/3 times pi times my radius of small, which is 4 squared, times my height of the small one, which was 10, and I'm going to do that in one go on my calculator and see what I get. Okay, put that into my calculator, and what I got was 380 over 3 pi, and just that is to the nearest whole number. That is going to be 398, and that is going to be centimeters cubed to the nearest whole. Okay, next thing I've got to do is find the surface area, and let's have a wee look at our surface area. So our surface area, we have got this curved surface area, and the curved surface area is going to be the curved surface area of the big minus the curved surface area of the small. And what we also have, which a lot of people will forget, is you've got this small circle, and you've got this bigger circle on the base as well. So just be very careful not to forget those. So what we've got is, I'm just going to put in brackets, curved surface area, CSA, of the big minus curved surface area of the small, and then plus you've got the small circle, which is going to be pi times 4 squared, plus you've got the the bigger circle, I should say, the bigger circular base, pi times 6 squared. So we're going to have to work all of that out. So the curved surface area of the big is going to be pi times 6 times its slant height, which was 3 root 27, minus, then the curved surface of small is pi times 4 times, and it was 2 root 29, I should have said, and then plus you've got 4 squared times pi, which is going to be 16 pi, plus 16 squared times pi, which is going to be 36 pi. Okay, that is, I'll have to zoom out a wee bit here. That's what you've got to do, so it's an awful lot to get sorted out. So we've got pi times 6 times 3 times root of 29, then minus the pi times 4 times 2 times root of 29. Okay, and then just plus 16 pi plus another 36 pi. Put that all into calculator, press equals. What I have got is 332.5, so I'm going to say it's 332 centimeters squared, and that is to the nearest whole, as was my volume earlier on. And that is it, done. Okay, we're going to look at this example again. Same example, we're going to just look at it a slightly different way. And we're going to be using the fact that you've got different scale factors for area and volume. This is going to be a quicker method, but I'd imagine most of you would prefer the method that I did first of all. So, we're going to look at the scale factors and the radiuses for from 4 goes to 6, and we got there by multiplying by 1.5. So 4 times 1.5 gives you 6. So that's how you get from small to big when we're talking about lengths. So let's just say for length, small to big, you multiply by 1.5. For area then, to get from small to big, you don't multiply by 1.5, you multiply by 1.5 squared. And for volume, to get from small to big, you don't multiply by 1.5 or 1.5 squared, it's 1.5 cubed. So the scale factor for length, square it to get the scale factor for volume, and cube your scale factor for length. Sorry, the scale factor for length, square it to get the scale factor for area, and your scale factor for length gets cubed to get your scale factor for volume. So that means if I can find the volume of this small cone, then I can find the volume of this big cone. And also, if I can find the curved surface area, so this curved surface area of the small cone, I can find the whole curved surface area of the big cone as well. So it will save us a wee bit of time. It'll be a wee bit quicker than the way I did it last time. But if you don't like this method, stick with the last method. It is absolutely fine. Okay, first thing we need to do is find the height and also then the corresponding lengths as well. So similar to what we did in the last part of the video, so I'll speed through this. So we have our height, h, of the small cone. So h, it's a length, so it gets multiplied by 1.5 to give me the total height of the big cone, which is h plus 5. So that's 1.5h is equal to h plus 5, which means 0.5h is equal to 5. And 5 divided by 0.5 is 10, and that's going to be centimeters. So I know my height of my small cone is 10. Also, I'm going to find L1, which is the slant height of the small cone, and that should be all. Using this method, that should be all that I need to do to be able to find everything I need. So L1 is, by Pythagoras, is going to be equal to 10 squared plus 4 squared, and square root, we did this before, so that was square root of 116. Put that into your calculator, it comes out as 2 root 29. So that's my L1. Okay, we are good to get started here. We've got all the dimensions that we need. Okay, so the volume of the small cone equals 1/3 times pi times my r, which is 4, and it gets squared, times my height, and I've just worked my height out to be 10. So that is 1/3 times pi times 4 squared times 10. Sorry, that is 160 over 3 pi. Okay, my volume of my big cone then is equal to k cubed, which is my scale factor cubed, so 1.5 cubed times 160 over 3 pi. And if we do that, 1.5 cubed times my previous answer, which was 160 over 3 times pi, that gives me 180 pi. So my volume overall is 180 pi minus 160 over 3 pi. So that works out to be 380 over 3 pi. And I think I had to give my answer to the nearest whole number, which is 398 centimeters cubed to the nearest whole. Okay, next thing I'm going to do is got to find the whole surface area. So I'm going to find the curved surface area of the small, which remember is pi RL. So pi times, and what is the radius of the small? The radius of the small is 4. The L of the small, the slant height of the small, is 2 root 29. So I'm not really using my calculator here. I'm saying 4 times 2 is 8. So 8 root 29 times pi. If I did that in my calculator, it'll give me a decimal. Leave it in this form, it's exact, it's perfect. And then that means the curved surface area of the big is 1.5 squared this time, because we're dealing with surface area, times 8 root 29 times pi. So that answer times 1.5 squared. And that is just going to be 18 root 29 times pi. So again, two exact perfect answers so far. And my total surface area, my surface area then that I'm looking for is the curved surface area of the big minus the curved surface area of the small, and then plus, just like in the previous way of doing it, you have to add on the small circular base. So small circular base is pi times 4 squared plus the big circular base, which is pi times 6 squared, and we put those things all together. So the curved surface of the big minus the curved surface area of the small is going to be 10 root 29 pi, and then plus I've got 16 pi plus 36 pi, and then let's just work this all out and see what we get. So you have got, what was that, 10 times root 29, and then that's being multiplied by pi, and then plus I've got my 16 lots of pi, plus I've got another 36 lots of pi, and that works out to be 332.5, so 333, it's going to be centimeters squared to the nearest whole. Okay, so that is difficult, quicker maybe, but difficult. But if you prefer the first way of doing it, all well and good.